Hello, so today we are going to do this problem, which is part of Leetcode daily challenge. So basically what we have, it's called binary search. We have an array of numbers that is sorted, and we have a target value. And what we want is to find this target value in the array. If it exists, we want to return its index. If it doesn't exist, we just want to return -1, right? And they want us to write it in O of log n, right? So not in O of n, because O of n would be easy, just traverse and find it, right? So pretty much when they say they want O of log n and they say it's already sorted, so that means they want us to use binary search. So how can we do it with binary search? Okay, so how do we handle this? So the idea here that I'm going to explain is using a more generalized version of binary search. You could of course just use Python bisect function, or if you are in Java, arrays.binary search, right? So that should be straightforward to do. But I like with binary search to use a general way to solve it, so that it's easy to extend and generalize to other variant than just finding a target value, right? And so in this case with binary search, what you will find this in all of the explanations I do is I try to find a function that is monotonic, right? So that means basically a function that either it starts out as false and keeps being false, or it starts out as true and keeps being after that it becomes false at some point. And this is the values of the function that we are going to do. And the x's are the input, right? The x is basically as x increases, if once it becomes false, it keeps being false, or once it becomes true, it keeps being true. In general, in most cases, it's going to be the first option, and so that's what will be in this case. And so what function that we need to do that can have this pattern, and the usual way to find the solution is that you are either looking for the last false value of the function, or you are looking for the first true value, right? That's the general idea. So here in our case, our function can be just that the number at that position is bigger or equal to target. Now why would this be monotonic? Because for smaller numbers, because the list is sorted, let's say target was 9 in the first example and the array was -1, 0, 3, 5, 9, 12, right? So for the first values, it's false for -1 because it's false for index 0, right? 4, 5. So it's false for index 0 because it's smaller, false for index 1, false for index 2, false for index 3, but it's bigger or equal, so it's true for index 4 and true for 12. Why does it always continue being true? Well, because the array is sorted, so as we progress, we will increase the value, right? And so since the current value is bigger or equal to target, then as we progress, we will only get bigger, so we will maintain that it's bigger or equal. So that means it has this property. So that means this is the function we will be using. The other thing to note is, to avoid having any boundary issues, you put low, you initialize your low and high values in invalid positions. So what do I mean by that? So what's the lowest invalid position here? That's -1. What's the highest invalid position here? Well, the after index, the last index, which is 6. So we just put 6 is just the length of the array, right? So let's call this the length. Let's call this array. It's going to be the length of the array. So this is how we initialize them. And with binary search, again, to avoid having problems, because binary search is tricky, you might have issues like either your loop not end, or for edge values, the value will be incorrect. What we'll want to do is we'll maintain an invariant that f of low is always false. So as we move low, we will maintain that invariant, and for high, as we move high, we'll maintain the invariant that it's always true. So that's the rule here. And that means, and we stop when the difference between low and high is just 1. So basically we stop when low is here and high is here. That's where we stop. So that's the idea. And so what is this? This is just a high minus low bigger than 1, equal to 1, right? And so this means we keep going as long as it's bigger than 1, we keep going. because low starts here and high starts somewhere here. We will keep getting them closer together until the difference is just 1, right? Okay, so that's now with binary search. Once you know the function you are going to check, once you know the low and high value, it's pretty easy. The only thing left to do is to know how do you move low and high values. So let me show that. So let's say we evaluate a mid and we find that it's false. So if we evaluate and find that mid is false, so somewhere here maybe, then that means what we want is we want our low value to be put here. There is no use in checking here because these are false values before mid, right? And we shouldn't put it at mid plus 1 because what if mid was actually here? We don't know. Then if we do it at mid plus 1 here, then we violate our invariant that the function on low value needs to be false. And so that we just put it in exactly at the position of mid. Okay, so if it's false, we just assign low to be equal to mid. Now what about if mid was the function of mid, f of mid was true? What should we do? Well, if it was true, then in that case we don't know, either it's here or maybe it's here. In the case where it's here, we should put high here, right? Because what we want is we want to get the high to be in the first true and low to be in the last false, right? And so we don't know if this mid was the first true, because maybe it was here. That the function just tells us that it's true. We don't know. And so that's why we put it at high and not at high at mid and not at mid minus 1, because if we put it at mid minus 1 and mid was here, we'll end up putting high at false. We will violate our invariant here, right? And so here, if it's true, we put high equal to mid. And this method is really good because there are no plus 1 or minus 1 to remember, right? If it's false, we want to maintain the invariant of f of low equal to false, so we set low to mid. If it's true, we want to maintain high equal to true, and so you put mid there. So that makes it extremely easy to write binary search. And so this is how we are going to write our binary search. The only thing we are going to do is that, because we don't know if the first true here was actually equal or just, let's say if it was 10 here, right? Then we'll still get this index 4 at the end of our binary search, right? Because our function just says bigger or equal. And so we just need to check to make sure if this 10 is equal to the target, then if the value at high is equal to target, which is the first true, then we can return high. But if it's not, that means the target is not in the array, so we can just return -1. So that's just a small thing to do at the end. But roughly that's the idea here with binary search, and the time complexity is of course going to be O of log n, and no space complexity, so O of 1 space. Yeah, so that's roughly it. Now let's implement it and make sure it passes test cases. Okay, so let's implement the solution we just saw in the overview. So what we need is both low and high value. We said we are going to pick the boundaries, right? So that there is no issue there. And then while we said high minus low bigger than 1, so while the difference is more than 1, we want to stop when the difference is just 1 because they are next to each other. And then we take our mid. To avoid overflow, we will do it division by 2 in binary, like this. And then if the number at mid is bigger or equal to target, this is equivalent to basically f of mid is true, right? This is equivalent to that. Because our f of x is that number at x is bigger or equal to target. So if this is the case, we want to maintain that high, the value f of high is true, and so we just put mid. Otherwise, we want to, it's false, so low is the one, f of low is the one that needs to be false, so we assign mid there. And that's pretty much it. Now, the smallest value, right, bigger or equal to target, in this case is nums of high. That's at the end of the binary search, this is what would be the case. And so we only want to check if this value is equal to target. That means we can return high as the index. If it's not equal to target, that means the target is not in the array, so we return -1. So to do that, if either high is bigger or equal to n, right, maybe this happens if the entire array is smaller than target, right, or the number at high is different than target, that means target is not in the array, so we can return -1. Otherwise, the index high is the actual index where the target value is. So we can just run this, except let's call this n. Let's define it like that. The length of the array. Let's submit. And this passes correctly. Yeah, so that's pretty much it for this problem. Please like and subscribe, and see you on the next one. Bye.